where we established that this result right here is true using the Cauchy-Schwarz. This reads the sine of x, sine to the fourth power, cosine to the fourth power is greater than or equal to 1/2. And let me just back up real quick and show you that. I won't go through the details, but here's the proof of it. We use Cauchy-Schwarz in a slightly different formulation. Anyway, we got that 1/2 is a lower bound for sine to the fourth power plus cosine to the fourth power. And it's fairly straightforward. We were able to just select C and D as 1 as a matter of convenience, and that's where the 2 popped out. And actually, you can graph this and see that this expression never gets any less than 1/2 globally. Usually, I just do it on the interval 0 to pi or 0 to 2 pi. But globally, the graph of this function never falls below 1/2. Now, we're going to take this just to be a fact at this point, and we're going to use that to actually carry this further. And of course, this can be generalized. It turns out there's always, ends up being 1/8 if this is to the 8th power, and so on and so forth. But anyway, let's go through it one more time because I used a slightly different formulation, a summation formulation for the Cauchy-Schwarz that you can see right here. This is another formulation for the Cauchy-Schwarz. Now, this has been hard on me to understand how this really works, but the idea is to try to take the expression and rewrite it in a fashion where you can get it expressed in terms of the left-hand side right here. Okay, in other words, if you can figure out a way to get this expressed in a way where you can make it look like this left-hand side, then you can write an expression for the right-hand side where you'll have an inequality. All right, and so in this particular case, I wrote down something dead obvious right here. Although you're going, what? You know, why does that work? But notice this result right here is definitely a well-known identity from trigonometry. It's always equal to 1. Let me get this thing working here, this marker. Okay, so again, this expression right here is just always equal to 1, right? It's Pythagorean's identity. It's the trig version of the unit circle. But again, this circled expression is just always equal to 1, right? And so that makes things kind of nice because if you manipulate it accordingly, you can actually make it fit this Cauchy-Schwarz condition. You see, I rewrote this as sine of x cubed quantity squared, right? You see, why did I do that? Because you see we have a square here. See this squared object right here and this squared object right here, okay? So that's exactly why we did what we did right here. We see we have square, 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 sum. Well, that's what this is. This is a summation, and it's the product of some summations, right? So that leads to this assignment of variables. A sub 1 is sine cubed, A sub 2 is cosine cubed, B sub 1 is sine x, and B sub 2 is cosine x. And I have to write it down. When I read about this, some people just can see it and write down the result, but I have to actually write down this. Maybe I'll get better at it at some point. But you'll notice right here, I color-coded this so you guys can see what's going on right here. It helped me. This summation piece right here is exactly the same as this summation piece right here. Notice how I wrote it out. You know, A sub 1 is sine cubed. A sub 2 is cosine cubed. And it just multiplies out very nicely here. Of course, this piece right here ends up being sine, the more conventional notation, sine to the fourth power, right? All right, and then of course this is cosine to the fourth power right here. All right, and again, as a fact, from the previous video that I did, we see that this is bounded below by 1/2. So you see it can get replaced right here. It can get replaced with 1/2, and the result follows. And again, if you were to graph this, you would see this ends up happening right around. It happens at pi over 4. And let's just say that x was equal to pi over 4. I'll show you guys this real quick. You may have already done it, but so if x is equal to pi over 4 radians, if x is equal to power 4 radians, we know that the sine of power 4 and the cosine of 4 is root 2 over 2. So what you actually get right here, and again, I guess I'll just put it right up here. Okay, that makes a little more sense. So we'll put root 2 over 2 raised to the 6th power. Okay, now that is root 2 over 2 raised to the 6th power, but notice, again, that's going to be the same as this right here, right? The cosine and sine agree at power 4. But root 2 raised to the 6th power would be what, 8? So we have 8 divided by now 2 to the 6th is what, 64? 2 raised to the 6th power is 2 times 2 times 2 times 2. 6 times that's 64. And so you get 8 over 64, which is what, 1/8? Okay, a 1/8. But again, that happening twice, okay, that's equal to 1/8. Sorry, right there. That's equal to 1/8. But the same thing would happen for cosine, right? And so you would have 1/8 plus 1/8 is actually the 1/2 that you see right here. And then so you have 1/2 squared is 1/4. Anyway, I'm still kind of battling this Cauchy-Schwarz stuff. I don't really always recognize the form that well, and so that's why I'm having to do it this way. But I hope you guys like that. And again, this can be generalized. I think for sine to the 8th power, cosine to the 8th power, that would be greater than or equal to 1/8, and so on and so forth. So it's something that you kind of think can inductively generalize. All right, thanks.